Okay, so let's proceed. Well, first let me very briefly review what we did last time. Last time we talked about strain. So strain is a concept that we already knew from 231 and 232, but the particular relation between the displacement and the strain was something that we did not explicitly think about at that time. So what we've done last time is we have defined a quantity h, which is the displacement gradient. So it has the gradient of the displacement field throughout the structure that we're trying to analyze. So u here is a function of, so we say u is u of x, it's a function of x, and actually also time. But very soon I'm going to, if not necessary, I'm going to omit the explicit dependence on time, because most of the difficulties that we will be facing, they have to do with the spatial dependence of the displacement field and not with the temporal dependence. So time is also there, but often I will omit it. So that's the displacement field, and the displacement gradient is therefore hij ui comma j. Okay, but that's just the displacement gradient, and what we need is the strain. The strain is eventually what is needed to define stress, and stress governs equilibrium. So from displacement to strain to stress to equilibrium, that's the path that we would like to take. And the strain is defined as 1/2 h plus h transpose, or in components, epsilon ij is 1/2 ui comma j plus uj comma I, right? So, and then we said, well, how is this related to the displacement concept that we already know from 231? Although we did not explicitly derive these sort of derivative relationships, I have analyzed and I've shown you that, for instance, epsilon 1 is simply u1 comma 1, and that very well correlates with, at least graphically, what we did in 231. And on the other hand, epsilon 2 is 1/2 u1 comma 2 plus u2 comma 1. And this object, this part of epsilon 2 is gamma 2. Okay, so in other words, what we used to do and what we used to call gamma 2 in 231 and 232, that's really twice the shear strain. We also used to call this shear strain, but now, from now on, the shear strain that we are going to use is epsilon 2. And the reason we're doing that is so that both the normal and the shear strains come from directly the same expression. It's sort of mathematical convenience, okay? So that's pretty much what we've done last time, if you skip all the details. So now this lecture, I'd like to talk about strain a little bit more, and in fact, with introducing something that is very similar to the strain, except that instead of a plus sign, I will have here a minus sign. So instead of adding h and h transpose, why not subtract? Does that give us anything at all? Is it useful? Let's talk about that briefly. Okay, so let's talk about the rotation matrix. So essentially, there is one thing that I'd like to now demonstrate, and that point is that strain does not reflect rigid body motion. And I'd like to now tell you what this means with two examples. Okay, and just for simplicity, I am going to consider 2D. I'll omit the u3 component and derivatives with respect to x3 as well. And I will give you two examples. The first example, to rigid body motion, so-called rigid body motion, is translation. That is fairly straightforward. Let's say I have a coordinate system, x2, x1, and the object initially rests near the origin. Okay. Let's say that's 1 and 2. And now what happens is that this object gets translated up and right by a certain amount. Okay. So that is, let's say, A, and that is B. Okay? So that's all it's doing. It's not changing its shape. It's not, let's say, rotating, it's just being translated. So if you would like to write the displacement field for this type of motion, first we realize that the current position of any point in the x direction is simply x1 plus a. In the y2 direction, it is equal to x2 plus b. And therefore, the displacement field is a constant actually in this case. In other words, normally it depends on the particular position we're looking at. But in this case, u1 and u2, they're both constants, and they are respectively a and b. Okay? So that's a simple setup. So let's calculate just for completeness what the displacement gradient and the strain matrices are. So it's good to practice at this point with the explicit representations of these matrices. So I'll just remind you, Hij is ui comma j. Now in this case, both u's are constants. So if you go ahead and take these derivatives, you're going to get a big 0. And therefore, epsilon, it is that plus is transpose over 2, 0 plus 0 over 2. So that's 0 as well. Okay, so here we make two observations. One, if the body, if the object that we're considering, the structure, gets only translated as a rigid body, okay, then the strain is identically 0. Okay? Not only is the strain is 0, h, the displacement gradient, is also 0 in this particular case. So let's make a note of that too. So the strain does not reflect rigid body translation. H also does not reflect rigid body translation. Okay, strain does not, H also does not. So that's example number 1. Okay, that's the simpler example. So now let's look at the second type of rigid body motion, which is rotation. Now I want to immediately here highlight that the rotation that we are going to talk about is small rotation, and that's important. And so let's construct an example for rotation. Again, I'll take the same object. Okay. So what I'd like to do now is I'll take this body and this square, I will rotate it about the origin. Okay, so if I draw a circle about the origin, right, everything is going to sort of rotate about the circle. So this thing will get a new shape like this, or a new orientation, let me say, like this. And so that's the new shape. And this here is, let's say, is the angle of rotation, beta. Now I've exaggerated the rotation, okay? So I want it to be eventually small. So I'll enforce that mathematically just very soon. But before I do that, let me write down the current position of any point within this original square after rotation, okay? So this is something you can verify yourself. So if the original coordinates are x1 and x2, the new coordinates are given by, for this type of a counterclockwise rotation. So that's minus sine beta x2, and y2 is given by sine beta x1 plus cosine beta x2. Okay, so that's what the new position of any point looks like. Okay, so now I enforce the fact that beta is small. Small with respect to what? Pi. Okay, so it's not going to be pi over 2. It's not going to be pi over 3. It's going to be, let's say, pi over 20, something, or pi over 100, something small. Okay. And that is needed because in this course, as I have emphasized several times, we are interested in small deformations. Okay, so the rotation has to be small for the displacements to be small. So Now u1 is y1 minus x1, right? u2 is y2 minus x2. Right? So if beta is small, cosine beta is 1, minus sine beta is minus beta, okay, for a small angular approximation. So this minus x1 is simply minus beta x2. And for u2, this is beta, this is 1, minus x2, it cancels that one, it's going to be beta x1. Okay, so this is the displacement for a small angular approximation. The displacement field is now not constant. Okay. All right, so now let's go ahead and, like we did last time, calculate the components of the first displacement gradient. So that is going to be the first entry u1 comma 1, right? It's 0. u1 comma 2, it's minus beta. u2 comma 1, it's beta. And u2 comma 2, it's 0. Okay. All right, so it turns out that although H does not reflect rigid body translation, it does reflect rigid body rotation. So let's make a note of that. So H does reflect rotation. But now let's have a look at epsilon. Okay, so this is not 0, but the strain, epsilon, is equal to 1/2 H plus H transpose, right? And let me write H transpose here so that we can sum easily. H transpose is 0 minus beta, beta 0. Okay, so now I sum up simply the entries. So 0, the first entry is 0. The second entry minus beta, beta, it's also 0. And then we have beta minus beta, also 0, 0, 0, also 0. So epsilon is perfectly 0. H is not 0, but epsilon is 0. Okay. Right, so the point here is that for small rotations, rigid body rotations, epsilon also does not show that. It does not display it. Okay? And indeed, I mean, that's something we want. Okay? We want that because if I rotate something, I'm not putting any stress on it. It just changes its orientation. Something will try to will get stressed, right? Stress depends on strain. It will get stressed if I try to, let's say, bend it. Then it will get stressed. But if I just rotate it, it should not get stressed. Stress depends on strain, and therefore, for stress to be 0, strain better be 0. That's sort of the argument. So this is actually a result that we desire, so it's good. That's what I wanted to show. Now, however, you must be careful. I did assume a small rotation that was necessary to go from here to there and eventually get this result. If the rotation is large, so it's not small, but I take an object and rotate it a lot. So in other words, if you go here and try to calculate the displacement field without this approximation by retaining the cosine and sines, you will actually find that epsilon is not equal to 0. So that's a homework problem. All right. So to get a meaningful result, to sort of correlate with our expectation that in our analysis, small rotations or rotations should not cause stresses, we have to make sure that rotations are actually small. Okay? And that's why we are making this assumption here. Okay. Okay, so that's good. We got that out of the way. Now, you might now ask yourself, okay, epsilon does not reflect rotation. H does. But in the definition of epsilon, I had a plus. If I switch that to minus sign, what happens? Do I get some new quantity? Is that useful at all? Okay? Indeed, we will get a new quantity, and it is actually useful. We are going to make use of it, not a lot, but in the few times that we will make use of it, it will be super useful. So let's go ahead and therefore define a new quantity, okay, which is what we're going to call the rotation matrix. Okay, I'm going to call that omega. Right? And omega is, as I said, it's very much like strain. The only difference is that instead of a plus sign, I have here a minus sign, H minus H transpose. So if you look at the components of omega, it's equal to 1/2 ui comma j minus uj comma I. That's what omega looks like. Okay. And so you can go ahead and calculate or write down the components of omega as well. Now there's something peculiar about omega due to the presence of the minus sign. So I'm going to write down the components. So that's what makes slightly different from strain, right? So 1, component here has 1, 1 minus 1, 1, 1 is 0. Okay. Likewise, 2, 2 is also 0. 3, 3 is also 0. Okay. And then, so the 1, 2 component is 1, 2 minus 2, 1, not necessarily 0. Let me write here omega 1, 2, and here I will write omega 1, 3, and here omega 2, 3. Now, let's compare omega 1, 2, and 2, 1. Okay. Omega 1, 2 is equal to 1/2 u1, 2 minus u2, 1. Whereas omega 2, 1 is equal to 1/2 u2, 1 minus u1, 2. Right? So essentially, the order of these two quantities, they have been switched. So this is equal to minus omega 1, 2, actually. Okay. So in other words, what I have here is omega 1, 2, and here minus omega 1, 3, and here minus omega 2, 3. Okay, so now this is very much like strain, but these zeros make a big difference. Strain, it's a symmetric matrix, so it has 6 independent components. This one, on the other hand, it's called skew symmetric. So a skew symmetric matrix has zeros on the diagonal. And when you look at off-diagonal components, 1, 2 is equal to minus 2, 1. Okay, that's the definition of a skew-symmetric matrix. So due to that, the skew-symmetric matrix has 3 independent components. Okay, if you know only these 3, then you know everything about the matrix. So because it has 3 independent components, if you like, it's almost like a vector. A vector has 3 independent components, right? And sometimes one makes use of that. Okay, we're not going to, but let's just keep in mind that qualitatively, a skew-symmetric matrix is almost like a vector. Now, for this particular example, we can go ahead and now calculate what the rotation matrix is. So for our example, which is this one, omega is equal to, so that's 1/2. Or let me write directly what it is. Okay, so it's H minus H transpose. So this time, so the diagonals, they are 0. Let me write down automatically, they are supposed to be 0. We have a 2D example. And then H minus H transpose over 2, minus beta, minus 2 beta over 2, minus beta. And here, beta minus beta, so 2 beta over 2, that's a beta. Okay, so that's what the rotation matrix looks like. So for this particular example, for this very special example where there is only a small rigid body rotation, H and omega happen to be the same. This is just a coincidence. In general, omega and H, and therefore H and strain, everything in general will be different. Okay? So I'll just make a note of that. This is just coincidence. Okay? What I would like to note at this point is this entry, omega 2,1. And omega 2,1 is equal to 1/2 u2, 1 minus u1, 2. Okay? That's omega 2,1. Now, omega 2,1 is, in this example, it is very clear, it's beta and it represents the counterclockwise rotation of the object. It's rotating about the out of plane direction, which in this case is x3. So the rotation about x3 is beta, and omega 21 is equal to beta. So this is, in general, will always be true. Omega 21 for such a planar, a x1, x2 plane rotation, with or without additional deformation, in other words, whether or not strain is equal to 0, will tell us something about the rotation in that region. Okay, so we'll make use of that. Okay, I'm making a note of it here. It belongs here. When the time comes to make use of it, I will remind you once again how we're going to make use of it. Okay, so now we have the strain matrix. We have the rotation matrix. So let's go ahead and apply it to a problem where there is both rigid body rotation sort of are involved together with deformations. And it's an example. It's a problem that we already are familiar with. We're just going to look at it from the perspective of this course. So it is the torsion of a cylindrical bar. This problem I have borrowed from your online reference. So let me write down what we're trying to do. So we are given the displacement field. In a homogeneous meaning there is only one type of material involved within the structure. It's not a composite, for instance. It is isotropic versus anisotropic. Circular shaft, that's the geometry. And we take a circular shaft and we twist one end through an angle while we keep the other end fixed. And the angle of twist is alpha. And I'm going to assume that this alpha is small so that eventually we have small displacements. Okay. So the displacement field for such a problem is, we have actually sort of already in this problem written something very closely related to it, but let me write down explicitly what it is now. So it is cosine. I'll introduce the parameters in a second. Okay, so let me draw the geometry. It's going to clear up some things. So, okay, so that's the circular shaft. It's fixed at one end. The length is L, right? And let's say this is our coordinate system, x1, x2, and well, let's write that over here to pick as our origin. So that is x1, this is x2, and the longitudinal direction, it's x3. Right. And the radius, I'm going to call C. And we will pick initially 2 points, points A and B. And what will happen is now we are going to twist the end through an angle alpha So now that's alpha. We are going to twist the end while keeping this end fixed, and therefore A will move to a new point A prime, and B will move to a new point B prime. So that's B prime, and that's A prime. Okay. And for this type of a deformation, this is what the displacement field looks like. Whether or not alpha actually is small. Even if it's large, this is what it looks like. But now we're going to simplify it by assuming that alpha is small. Okay? Now, U3 in this case, it's 0. So there will be no displacement in the 3 direction. I'm just twisting the end. So all the displacements at any cross section, it is fixed to the x1, x2 plane. All right? So circular cross sections remain planar and circular. Okay. So let's analyze this deformation. Now, alpha is the twist at this end, right? So this end twists by an angle alpha. This end is fixed. So it does not twist at all. So that's why the rotation is parametrized like this. If x3 is equal to L, I'm at that end, the rotation is alpha. If x3 is equal to 0, this thing is 0, there is no rotation. And in between, the angle of rotation linearly increases from the fixed end to the free end, or the twisted end. Okay? So let me call this beta. This thing eventually needs to be small, and if alpha is small, x3 goes from 0 to L. If alpha is small, beta for sure, it will be small, right? So here, always what I have is beta here as well, and there as well. Okay? So let's proceed with that explicit assumption. Okay, so we'd like to essentially eventually analyze the deformation. Okay, so since alpha is much, much less than pi, beta is also much, much less than pi. So we can go ahead and simplify U1, U2, and U3. So when beta is small, this is 1. 1 minus 1 is gone, 0. And this is approximately minus beta. So minus alpha x3 over L x2. And if I look at U2, this is approximately beta, alpha x3 over L x1. And the second one, because this is approximately 1, it vanishes. Okay. And U3 is equal to 0. So now so I've got the displacement field. I want to also calculate the displacement gradient, the strain, etc. So H is the displacement gradient. Hij is ui comma xj. So let's go ahead and do that together. So we have H. Okay, so 1 comma 1, that's a 0. 1 comma 2 minus x3 alpha x3 over L. 1 comma 3 minus alpha over L x2. 2 comma 1, it's alpha x3 over L. 2 comma 2 is 0. 2 comma 3 is also equal to 0. And the third entry is 0 by construction. So that's H. Let's also write down H transpose to make our calculations a bit easier. So H transpose is 0 minus alpha x3 over L, alpha L x2, alpha x3 over L, 0, 0, 0, 0, 0. Do you have questions so far, by the way? Any question? Yes. U2, comma, 3 elements should not be 0. Thank you. So it's alpha over L x1. And therefore, yes, thanks. Okay, so let's go ahead and calculate epsilon. So I'm repeatedly writing down the expressions. So at some point, we need to learn what they are, the basic ones. So epsilon, H plus H transpose over 2. So strain, okay. So the diagonal entries are conveniently equal to 0. I can directly write those. And then that plus that, that's a 0. And this, that's a 0, so it's minus alpha over 2L x2. That's the 1, 3 entry. And then the 2, 1 entry, that plus that is equal to 0, right? That's a 0. And the last entry is alpha over 2L x1. And since this row is 0, I just need to divide that row by 2. And in fact, I don't need to do anything because epsilon is supposed to be symmetric. So I can just simply copy over those entries. Okay. So that is the strain matrix. Let's also calculate the rotation. Okay, so now this one minus that one divided by 2. Again, the diagonals are conveniently 0, 0, 0, 0. And this minus that one, so that is the same quantity divided by L only. Okay, it's the same thing. And then this minus that divided by 2, so it's the same as this entry, minus alpha over 2L over x2. And so let me proceed and finish it up. Actually, again, I'm almost done. Actually, I can go ahead and calculate this entry as well. So that minus that over 2, so this one divided by 2, alpha over 2L x1. And now I know that it has to be skew symmetric. In other words, this entry is minus that entry is minus that, this entry is minus that. Okay, just to speed up things. Pretty much everything is straightforward, right? We're practicing with both the definitions as well as the explicit enforcement of the fact that the deformations have to be small. So I have to enforce that and calculate the approximate, or let's say the field where the displacement is indeed enforced to be small. Afterwards, my calculations now are supposed to make sense. Okay. So if I don't enforce the small deformation, the meaning of epsilon in the context of this course will be violated in some sense. Okay, so I cannot eventually proceed with any type of analysis based on a wrong epsilon. Okay, so that's pretty much the point here. But I'd like to make another point here. So for that, I will, since I have the figure over here, U3 is equal to 0. There is nothing exciting about that. In fact, let me also erase this. I just want to retain the figure. Okay. And I'd like to talk about whether all of this correlates with what we have done in 231. Okay? So because in 231, if I had given you such a problem, with your knowledge, you would go ahead and calculate the gamma, the shear stress, etc., in a pretty straightforward manner. It's a rather simple problem in the context of 231. So let's see if all we have done makes sense with respect to our 231 knowledge. Okay? So right? So for that, I will pick these 2 points, A and B. Okay? So these points have eventually coordinates. Right? x1 for an A is, for instance, x1, x2, x3. It's equal to, right? It's radius is c. So this point has in the x1 direction c, in the x2 direction 0. So c 0, L. C 0, L. And the second point I'm going to look at, it's B. And at B, x1, x2, x3, that's equal to, in this case, the x coordinate is 0, x1 coordinate, x2 coordinate is c, so 0, c, and L. Okay. Right. And for these 2 cases, epsilon, let's have a look at the strain matrix. So for instance, A, C, 0, L, right? X2 is 0. So for at point A, this entry is 0. This entry, therefore, is also equal to 0. X1 is equal to L, so I have alpha over 2, alpha over 2. So everything is 0 except the 2, 3 entry, and the 3, 2 entry. They're supposed to be equal to one another. Sorry. X1 is equal to C, right? Sorry, alpha C over 2L. Alpha C over 2L. Okay. And at B, so we have 0 CL at B, 0 CL. So this one is 0, and that one is 0 for B. And x2 is equal to C for B, so it's minus alpha C over 2L minus alpha C over 2L. Okay, so now, in 231, we used to work with gamma as the shear strain. So gamma 1, 2 is equal to gamma 2, 3, sorry, is equal to gamma 3, 2. It doesn't matter which one I look at. And that is equal to twice epsilon 3, 2 in the context of this course. So it's equal to alpha C over L. Okay. So indeed, if you go to 231, and if you look at your lecture notes, and if you have such a geometry, a circular shaft twisted through an angle alpha at the end, radius is C, length is L, the shear strain at that end is equal to alpha C over L. So we were rarely directly interested in the particular component of the shear strain. We used to call this gamma max. Okay? Because the shear strain increases with the distance from the radius. Okay? In fact, in 231, we knew that it's alpha rho being the distance from the center, alpha rho over L. So if you are on the surface, it's equal to C, so it's alpha C over L. So that's an expression that we used to have. So likewise, for this case, we have gamma 1, 2. It's equal, sorry, gamma 1, 3 is equal to gamma 3, 1. And that is equal to twice epsilon 3, 1. And that is equal to minus alpha C over L. Okay? So that is equal to, or gamma max is equal to, epsilon 3, 1. Okay? So we were always directly looking at gamma max, and that one, we were not concerned with the sign. The maximum value is still equal to alpha C over L. Okay? So indeed, it doesn't matter whether you're looking at that point or that point or that point. Any point on the surface has a gamma max is equal to alpha c over L. Now, but remember, what does the direction eventually indicate? And we'll recall this once again when we talk about stress, so you will have a chance to recall, right? So for instance, 3, 2, right? So this is gamma max. And the shear stress, tau max, is equal to the shear strength, the shear modulus G times gamma max, right? Okay. So, and the component of gamma we're talking about, it's 3, 2, and therefore this will also be 3, 2. Okay. Now here, we have tau, all right? Tau max is equal to G gamma max, okay? And the component that we are particularly talking about is 3, 1. So tau 3, 1 is minus G gamma 3, 1. Okay, that's the explicit expression for the shear stress with the sign and with the particular exponent. So what does the sign indicate? Well, the sign indicates the following. So I am twisting. Right? So if you like, have a look here for a second, just sort of refresh your 231 knowledge. Right? I'm twisting counterclockwise. So at this point, let's pick the red color. So at this point, twist is up, so or counterclockwise, the shear stress is always tangential to the surface. So it should be upwards, right? That's the direction of twist. So this is a stress component. And remember, we always used to say, well, stress component takes 2 indices. The first index is I'm on the plane with normal 3 in the direction upwards 2. 3, 2. And if it is positive, it points upwards. So it is pointing upwards. It's supposed to be positive. And so shear stress, and therefore tau 3, 2 is positive. At this point, the twist, still it is right counterclockwise. So it's again tangential. I'm still on the plane with normal 3 in the direction minus x1. And therefore, it should be minus. And that's where this minus sign comes from. Okay? So all of these results, therefore, they are coming from an entirely different perspective, right? But the results are completely consistent with what we used to do. So we're just warming up with an application to what we need to know, what we used to know from 231, but we're approaching the problem from a different perspective. Okay? Okay, so questions about this problem? Right? So the reason, again, I'm giving this is so if you get lost in somehow the approach here, but we need to warm up to this kind of approach, you can sort of go back to 231, open up a simple problem, and sort of recall what the mechanics was. And then you can come back here and say, oh, OK, now I understand what this means, and so on and so forth. Okay, it might help you grasp the topic a little bit better. Oh, OK. So one thing that we often have a problem with is the direction of displacement. Okay? So for instance, at this point A is moving upwards. This point is moving leftwards, etc. Right? If I pull on this bar, it's going to move in the x3 direction. These are sort of perhaps not too hard. But let me give you some examples, and so that we can understand which component of the displacement field is non-zero in very specific problems, and where there is some symmetry. So we're not going to always use Cartesian coordinates. We're going to sometimes use cylindrical or spherical coordinates. So in those cases, we need to be able to understand which components are non-zero and which components are 0 from the outset. If something is 0 from the outset, it simplifies our life, right? Many of the entries in the matrices that we are dealing with will be 0 from the outset. So it will be easier to deal with the problem. Okay? So that's why now I'll give you some of these examples, and we try to figure out which displacement component we need to concentrate on. So while I'm erasing, let's talk a little bit. So if you have a balloon, and the balloons are not spherical, but let's imagine they are. You have a perfect spherical balloon, and you want to blow this up. Okay, you blow air into it, and so it starts expanding. Okay, You can, of course, always solve any problem in a Cartesian system, in principle. Okay? It might be nearly impossible, so hard that it's nearly impossible, but in principle, you should be able to. However, if you're analyzing that problem, which coordinate system would you use? Spherical. Okay. So in a spherical, now that's the easy part. So now the second part. So how many components does the displacement vector have? What are the components? Yeah, what are they in a spherical coordinate system? Huh? UR, U theta, U phi. Okay. Is any one, or perhaps are any two of these displacement components zero? Angle ones are zero. Can we visualize that in your minds? Excellent. Okay. So let me first draw that. Okay. That's a good start. Because if you can make that visualization from the outset, you start with problem way ahead of anyone else who assumes they are not zero. If you think they are not zero, you can still solve the problem, but it will take you much more effort to, or many more pages to attack the same problem. If you see from the outset that the only non-zero component is the radial component, things are much, much simpler. Okay? So that's what I aim to do here. So again, you can always solve any problem in a Cartesian system, but if you look for symmetry, if there is symmetry, right, there doesn't need to be one. But if there is symmetry, look for it and try to make use of it. Okay, so the first example, we have a sphere, and I will take a point on the sphere. Doesn't need to be located at any particular point. And let's say I take a cut. So this sphere is actually hollow, and it has some wall thickness. This wall thickness may or may not be small. And in fact, in this course, we're going to look at the case where the wall can be rather thick. Okay? That's something that we have not talked about before. Okay? In 232, we looked at the thin wall case. In this course, we will be able to look at the thick walled case. So there is some internal pressure. You pump air into it. And the deformation field is such that, and that's what we need to visualize, the deformation field will be outwards. Okay. Or displacement. Okay. So if you go ahead and you try to write down the displacement at, for instance, point A, it will have some functional relation on the problem parameters like the radius, the wall thickness, and I don't know, the pressure that you're applying, etc. But the point here is that if you try to use the Cartesian coordinate system for an arbitrary point, for a special point, some of the Cartesian components may be zero, but if you're looking at an arbitrary point, in general, all of the components will be non-zero. So you'll be dealing with three unknowns. But on the other hand, if you look at the spherical coordinate system, then you immediately get rid of the tangential components from the outset, right? And now I can only concentrate on UR, and that will simplify my life. Okay? All right, good. Now, what if, okay, so this is case one. Let's look at case two. And case two is I will take the ball, and if you like, I'm rolling on the surface. Okay, so I'm going to rotate it. Okay, let's say like this and like that. Okay. right? We're always talking about small displacement. So when I blow up, this displacement is exaggerated in the context of this course. It has to be small. Likewise, when I rotate, the rotation has to be small. But I'm talking about rotation without any inflation or without any shrinking. Okay? So in this particular case, if I look at the displacement field, is anything 0? The radial one is 0 in this case. Okay, good. This I don't need to worry about. Okay? If the rotations are small, then these are small. What will the strain be? Will it be stressed when I rotate it? It shouldn't. So what should the strain be? It should be 0. Why is it 0? Because I'm only rotating it small. Okay? Right. So this will be the displacement field, but it's not really an interesting problem from a mechanical perspective. Perhaps for dynamics it's interesting, but for mechanics I want to find out the stress field, and such a small rotation is not going to cause any stress field, so it's not so important for us. Okay, so another problem. So this is an example for the spherical coordinate system. Let's now give an example for a cylindrical coordinate system. Okay, so let's say this is a frictionless surface. So this time I take a cylinder, I put it onto a surface, and what I'm going to do is I'm going to press on it. When I press on it, it's going to try to spread, right? It's going to deform, but this surface is frictionless, so it can deform freely. It can slide freely on that surface. So it's not going to probably change its shape so much. To press on it, I put another plane at the top. It's also frictionless. And I eventually push down, all right? So now, let's pick a point, any point again. For some special points, if you use a Cartesian basis again, the displacement component, one of them, two of them, whatever, may happen to be 0. But I'm picking any point A. So for any point A, it's better to use the cylindrical coordinate system. And so for such a scenario, is anything 0? U theta is equal to 0. Right. Okay. So if I press down, it's going to spread. UZ, there is motion in the axial direction. There is spread that's going to be represented by UR. But things are not trying to rotate. If they try to rotate, if I take it and rotate it, only this will be non-zero. The others will be 0, etc. So what would be a case when UZ is 0? The following might be an example. So for instance, I put two planes, and these constrain motion in the Z direction. And then somehow I manage to blow air into this thing. So it will try to expand. But it cannot now move in the vertical direction. And in that case, UZ is additionally 0. Okay? And the only unknown I have would again be UR. Okay? So both planes fixed is trying to expand or contract. And there is no motion in the Z direction, only in the radial direction. So let me do this if inflated. Okay? Without pressing. All right, so that was yet another example. Let me give one more example. Well, actually, three more examples. So I have a circular shaft or a cylinder. It's fixed at one end, so it's attached. It's not frictionless or anything. It's completely adhered to that surface. And I'm interested in the displacement field, let's say, on the surface at point A. And what I'm doing is I am attaching, let's say, a string to a point at the end, and I'm going to pull on that string with a certain force. I'm going to pull on it. So this is an ideal point force. Of course, you can, it's an idealization. You cannot apply force at a point. It has to be, in the end, distributed over an area, small, but a finite area. But let's say it's a point force, okay? I attached a string, and I'm pulling on the string. So which coordinate system? Cartesian, okay? So if you use Cartesian point coordinate system, so this thing will for sure move there. It might try to sort of contract, right? So because it contracts, it means perhaps it gets closer to the axis. And when it moves in this plane. So U3 is non-zero because it's moving in that direction. And U1 and U2 are non-zero because it's contracting. So yes, you can. But nothing is zero. It doesn't simplify our life. Okay? So cylindrical is the obvious next candidate. And spherical is obviously not a candidate, right? So what is zero? Theta again is zero. Right? I say that in principle you can still solve the problem like this, but let me tell you, it's going to be nearly impossible, okay? If not impossible. Right? So you have to, in a sense, be able to see the symmetry. Then you'll be able to proceed with a solution that is effective, okay? One that we can relatively easily handle. So what does the displacement field look like after? I just want to sketch it sort of, right? So it's fixed at one end. And so I'm pulling on it. So due to Poisson effect, probably if the Poisson ratio is positive, so it's going to contract like this. So the more I pull, the thinner this side will be. This side is fixed, so it cannot get thinner. And on the other hand, it's a point force. So at this surface, there is going to be a strong deformation, perhaps like that. I'm exaggerating, of course. But at that point, I'm pulling. So the surface will also get significantly deformed. All right? So I don't know exactly how it will look. But the point is that UZ and UR, right? There's motion in that. And the radius gets thinner. But U theta, it's something you can omit. All right, good. Yet another example. So we're going to apply a torque. Okay. And let's look at this point A. And for that matter, you could be looking at any points along the, on the cross section or along the axis of this cylinder. But I'm looking at point A. So keep in mind that the torque has to be, let's say, comparatively small if the deformations are supposed to be small, right? So that's always an underlying assumption. So with that assumption, is anything zero? Do we agree with UR? How about this one? Okay, so, all right, so that's a fair remark. So it might shorten. I'm going to assume that it's isotropic. So think of 231. In 231, if I twist something, does it shorten? In the context of 231, it didn't, okay? Because I was assuming an isotropic material. If it's anisotropic, it might, okay? But so assuming isotropy, let us get rid of this part, okay? Now, she said UR, so let's think about it. Is U theta 0? Let's also think about that. Or is it not 0? So let me draw the cross section. And I'm looking at A, so I'm looking from the front. That was point A. Now, suppose I rotate this a lot. If I rotate this a lot, A will move from that point, let's say, all the way over there. So this would be the displacement vector, okay, for large rotation. Okay. Obviously, there is no symmetry here. This thing has a component along both r and theta directions, okay? But we're not looking at large rotations. We are looking at small rotations. When the rotations are small, A moves to a point that is very close by, okay, when it's idealized, right? So it moves to, let's say, that point. Perhaps that's even large, but let's idealize, and that's a close point, relatively close point. And now I look at the displacement vector from A to A prime. So this is the direction of that displacement, which is U theta, okay? So it has no, the smaller it is, the smaller the radial component is. And in fact, if the deformations are really small, or when we directly impose as it being from the outset as being small, this is 0 as well. And so the only thing that you have to deal with is U theta. Okay? So that would also simplify our life. All right? So now let's finish up with one final example. I have a bar, and I apply a bending moment at the end, and I'd like to analyze its deformation. So now, of course, you see that in all of the problems, the coordinate system you're using is naturally imposed by the geometric symmetry. So you have a cylinder, you try to see if you can use cylindrical. You may not be able to always, but you first try that. Okay, so here, obviously, there is no symmetry. So there being no symmetry, then you would say that, well, I have to proceed with a Cartesian coordinate system. There isn't much to do, right? So if we have such a problem, then we sort of have to stick to our good old coordinate system. Okay. You should also be aware that, for instance, you could take this problem, right? It has geometric symmetry, cylindrical. But now if I apply a bending moment to it, the deformation itself does not have a symmetry. So if I try to bend it, there is going to be also motion in the vertical direction. So so this coordinate system perhaps is not the best anymore. You just stick to this again. There will be, in general, a motion in every direction. So you, again, may want to fall back to a Cartesian one. Okay. So I gave you some examples. These examples are also fairly representative of what we are actually going to solve for in this course. Okay, so we are going to solve a thick-walled cylindrical pressure vessel problem and perhaps its variance. We are going to solve problems that look like disks or shafts, inflated tubes, and bending beams. And always, we will try to always move. So we need the methods of this course the approach of this course, because we are always going to try to move beyond the expectations, or let me say, not the expectations, but limitations of 231 and 232. For instance, we are going to look at torsion, but in 231, you always looked at the torsion of circular geometries. Okay? So it's not so exciting. We're actually not really going to do that. Instead, we're going to take, let's say, a triangular cross-section. So if I have a prism and if I try to torsion it, what will happen? It doesn't fit in the assumptions of 231. I need the methods of this course. If the pressure vessel has a thin wall, it's easy in 231, 232, we can tackle it. In this course, I look at the case when the wall is arbitrarily thick. I will take a beam. In 231, there was an intrinsic assumption that the beam is very long compared to its in-plane dimensions. What if it's not very long, right? How do we solve that problem, etc.? So we always are going to be able to attack problems that exceed the limitations of our previous, let me say, 231 framework. OK, so we have actually not much time remaining. I'm surprised, actually. We are out of time, 11:55, right? So let's stop then. And